Hi, everybody. So as Yasir said, I'm Caroline, and we'll be presenting today on securing the Android lock pattern from brute force attack. So everyone is quite familiar with the Android lock pattern, and cyber attacks on Android devices have increased in frequency and commonly occur in physical settings with a combination of shoulder surfing and brute force attacks. So like in a public area, someone might look over someone else's shoulder, get a glimpse of their password, and then if they can obtain that device, then they'll be able to brute force it with a little bit of an idea of what their password might be. And these attacks are more commonly seen in devices secured by the pattern lock mechanism rather than a PIN entry. So our work aims to investigate the various methods that increase the security of Android lock patterns. Some of the background research showed that these pattern locks are especially vulnerable due to users using one of a commonly used pattern set. To test this, we proposed a pattern matching algorithm that recognizes these common lock patterns and then increases a risk score if those passcodes are attempted. Next slide. So there is some research regarding shoulder surfing, but that typically focuses on the prevention of the attack and not the actual logistics of when an attack is going on. The paper featured on this slide is especially important to our work as it identified the 28 most commonly used Android patterns, and we use that for a data set when determining the risk score and everything. So other research on brute force currently shows that device locking systems are not sufficient and remain quite vulnerable with a high level of success in attempted attack simulation. So to better Android device security, we proposed a system that identifies the common patterns and lists them as a high security risk. Our system both denies the user from using these common patterns when setting up their device and monitors for an attacker trying to access the system by entering those patterns. As previously stated, our work aims to provide further protection for Android devices. Next slide. So our system utilizes a risk scoring system to determine if a device should lock after each attempt. The owner will set a pattern during setup, which is only accepted if it's not on that common pattern list. The user will also then establish their preferred risk acceptance level after an explanation of what that acceptance level means. So let's say you set your risk acceptance level to 10. One of those commonly used patterns might be a level 2, where one that's not so common and maybe similar to your actual entry might be 0.7. So then if it's a common password, we'll hit that risk acceptance level way faster than if it's just a slight miscalculation from what your actually your password is. So it gives a little bit more of a personalized user experience as you get to determine your risk acceptance. So our system uses a pattern matching algorithm to identify whether an inputted pattern matches a common pattern. Since the user cannot set a common pattern as their passcode, the attempt of these patterns is a high-risk action. Pattern matching also compares the current unlock attempts to the previous entry. Sequential unlock attempts with a big variation indicates that the user doesn't even know the password, and that indicates that it is an attack. And then actions deemed high risk will significantly raise the risk score, while actions that are low risk will only marginally raise it, like mentioned before. When the device becomes locked, it may be subject to a time penalty or require connection to a device at home. One solution for the locked out device is to have a recovery email tied to the account. Since attackers would not have access to the email link, the device would remain locked. And also, if a user is not currently using the device and they receive that email, it is a good indication that the device is being attacked. So our algorithm provides improved security compared to the previous research done on Android lock patterns, creating a cohesive interface that blocks the use of commonly used patterns and utilizing a risk score where users can enforce their security preference. Together, these both provide strengthened security for the device locking system.
So for development, we used Python. The TK interface package, which was used for the GUI, and the SMTP lib, which was used to send email verifications once a user was locked out for either if it was for a brute force attack or they just inputted the wrong pattern. So as you can see, so a common pattern usually signifies a high risk. We got these common patterns from the research Caroline just mentioned earlier, and we have implemented, we have put them into arrays, and if we saw a match to a common pattern, then the risk score would be high and it would increase. This would also result in the attempts to unlock the phone to reduce. So the more someone tries a commonly used pattern, the less tries they get. So for example, if someone uses a regular uncommon pattern, it would be 4 tries, but if someone uses a common pattern, it would be 2 tries instead. So if he doesn't get the correct pattern on the second try, the phone would be locked out. So an uncommon pattern signifies low risk, and then even if they get a wrong pattern, so they would still get half a point for the score, and that would still keep them, give them another chance to try to get access to their devices again. So yeah, the patterns are presented as arrays and from numbers 0 to 9. So as you could see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now the 0 just means that the pattern has ended. And then everything else is just actually an input on the pattern. So yeah, doing this allowed us to perform pattern matching by analyzing the position of numbers in the array and calculating how similar the arrangements were. So just to explain a bit of how the risk score is calculated. So let's say the pattern has, or the lock pattern consists of 5 like lock hits. So every correct lock hit is 1 point. Every incorrect lock hits that is not in the pattern is 0. And then if someone hits a lock pattern that is in the pattern, but it's not in the correct position, they would get half a point. So then this would be added up and then divided by the number of patterns they have hits. And then depending on that, if the accuracy is more than 75%, then they would get another chance, because the odds of someone getting 75% correctness of a lock pattern and higher is usually the user. If it's lower, then it's someone trying to brute force into the phone, or maybe just the user made a mistake, right? So they would get another chance. If the other chance wasn't correct, then the phone would be locked out. Now, so once the phone is locked out, as you can see in the picture here, an email verification is sent to the email that they have signed up with, and once they enter that, they would be able to gain access to their device again by having to retrying to bypass, to get the lock pattern correct. So yeah, so let's just show you a demo on how the common pattern block list and the email verification code system works. Can you see this video? Okay. And to make it fun. Yeah, so this is setting up the recovery email. So this process usually happens before is supposed to happen before someone sets their pattern. And then once they set a pattern, we can see that this is one of the most used patterns. It's the Z. So then the phone would prompt that this pattern is a commonly used lock pattern. So it would prompt you to try entering a different pattern. So once the pattern is accepted, trying to unlock the phone with just wrong patterns a few times would result in this. So you would have to go get your verification code from your email, input it in, and then you'd be able to access your device again. This video will demonstrate how to unlock unlock attempts with results and fewer available unlock attempts. So now we're setting the passcode. Yeah, so it could be 3 tries sometimes, it could be 4 tries, depending on the result of your first try, and then that would determine how many more tries you get and when the phone would be locked out. So instead of having a set number of tries for each unlock attempt, the number of unlock attempts changes as you input your first pattern. So that would just test if this person, that would test the average of the correctness of your pattern. If it's high, then it would give you more tries. If it's low, then it would limit to either 1 or 2. So we have tested our algorithm in different ways. So we got 12 users trying to shoulder surf and then brute force. So yeah, so most users weren't able to get to bypass this algorithm, and the phone had the phone would unlock right after a few tries. Now the feedback we got was 4 out of 5. We also tried different pattern lengths, and then how many tries before the attacker got locked out. And we saw as the number increases of lock patterns, the less tries it is. So we recommend using a passcode of a pattern length of at least 8. And then the feedback we got was 3.375 for increasing the password length, the pattern length. So for future work, we plan on testing with automated brute force attack as opposed to human attackers, as well as come up with new ways to raise the risk score, such as geolocation. If someone's trying to access your phone from home, then it's most likely someone that lives within your house, which is not as big of a deal as if it was someone accessing it from a different location. We also plan to use machine learning to help identify human behavior. And yeah, that's it for our presentation. Does anybody have any questions?